So now that I have told you that the ADC can be non-linear and it can generate harmonics, I expected a question from you. Since you are not asking, I'll ask the question myself and answer it. See, recollect the operation of quantization. Is it a linear operation or a non-linear operation? It's a non-linear operation. So we are dealing already with a non-linear block quantizer. So now when I say that the ADC is non-linear, what do I actually mean? Right? This should kind of pick your mind, like kind of like confuse you. If it's not confused yet, I mean you should be confused right now. And to understand this, let's actually look at the quantizer characteristic again. Okay. So here I am showing an 8-level quantizer, full scale range from -1 to +1. I have y-axis is the codes going from 0 to 7. Fine. This is an ideal quantizer. This is what we say linear, right? Although the quantization is non-linear, as of now, if I apply a sinusoid at the input, I'll only see the sinusoid and the noise, nothing else. Fine. So here, right, one thing to note is, if let us say, by the way, what is the ideal step size here? Delta ideal. I have a range from -1 to 1, total of 8 levels, 2 by, that is 0.25. Fine. So now let us say here I go and find the step size for each code, right? So let us say this is the code 1, I find this step size, call it delta 1, this is delta 2, and so on. What can you say about all of these deltas? Huh? They're all equal and equal to the ideal step size. Fine. And also these guys, these are called transition voltages. Again, this is -0.75. So let me just do it fully. This is +0.25. This will be +0.75. Okay. So this is the transition voltage for code 1. That is the voltage at which this fellow, sorry, this is for code 1. This is the voltage at which the characteristics jumps to code 1. This is the transition voltage for code 2, and so on. Okay. So now if I basically go and connect all of these transition voltages, what do I get? You get a straight line. So this is what we loosely say that the quantizer is linear. That is, the code width for all of the codes are equal, or other way of saying is, if I join all the transition voltages, we get a nice straight line. This basically means if I look at this characteristic from a long distance, it will look like a straight line. You will not see these jumps, you will kind of see a straight line. Okay. So now that we are here, let's just do a few things. So yeah, can you tell me the kth transition voltage? So in terms of K and delta. So easier thing to notice is, this is the transition voltage for code 4. For the code 4, the transition voltage is 0. For code 5, the transition voltage is 0.25, which is delta. Right? With this information, can you tell me, for code 4, transition voltage is 0. For the code 5, it is delta. Code 6, it will be 2 delta, and so on. From this, can you tell me what is Vk? K minus 4 times delta, right? That's fine. Fourth code it is 0, fifth code it is delta, sixth code is -2 delta. For the third code it is minus delta, right? So again you can see it's a straight line if I plot the transition voltage, right? And also if I take the difference between two successive transition voltage, what do I get? I get the step size delta. Is that okay? Cool. So bottom line, what do I mean when we say we have a so-called linear quantizer is this? The delta case will all be equal. So this means it is linear. This is the input voltage.
Okay.
This is the output code.
So that code is delta.
Which one? Tell me.
Code is delta.
Which one?
The code on the y.
No, delta, remember this is delta, okay? Delta is as units of volts, step size. So yeah, so it means that when I say we have a linear quantizer, all I mean is the code widths are equal for all the ports, or the other way to say is if I go and connect all the transition voltage, you get a nice straight line. Okay. So to this quantizer, if I feed in a sinusoid, I will not see technically the harmonics. Okay. Now if I have a nonlinear ADC due to circuit nonlinearities, I will basically have some nonlinear characteristic like this. That is, if I sketch or connect all the transition voltage, I will no longer have a exact straight line. I am grossly exaggerating and drawing. You will get a nonlinear curve like this. So here if you actually go and sketch this, let us say these are different codes, you will basically have something like this, the characteristic. So you will have something, oops, like this. This is how the characteristic will look like. Okay. So here you can clearly see the delta K for different codes, they are different. Is that okay? So, so that's what we mean when I say that we have a nonlinear quantizer, and here of course when you feed in a sinusoid you will get harmonics, and you can find the signal to noise and distortion ratio to quantify this and move on. But sometimes you are actually not interested in digitizing time varying signals. We might be interested in digitizing so-called static or DC signals, right? So in that case, I would like to see how nonlinear my ADC is when digitizing DC signals, loosely speaking. So for that, if you resort to this frequency spectrum, I will have input is DC, omega 0. So where the harmonics will lie now? All harmonics will be at DC. So you can't differentiate the signal and the harmonics. Fine. So it doesn't mean the ADC is nonlinear. It is nonlinear because as you see, I apply different things, you get a nonlinear thing like this. Just that for DC we can't rely on this frequency spectrum. For this kind of static nonlinear characterization, we have to actually explain how the quantizer characteristic is deviating from my ideal characteristic. That's the only way. Okay.
The code is the V output by delta itself, right?
Code is not that. Code is basically.
When we defined quantizer, we had an input Y over delta and V over delta.
Yeah. So not that. So here, let us say you get some V over delta. You have, let us say, discrete values for V over delta. I am giving a code. Let us say the lowest one is 0, next one is 1, and so on. This is technically it should, can also plot with V by delta, but this won't be 0, 1, 2, 3. This will be an appropriate value.
So can you define what code is?
Okay. So what I'm saying is, this is the thing. So ideally, let us say I plotted it with respect to V by delta here. Okay. So this will be something. This will not be 0, 1, 2, 3. This will be some voltage, right? So what I'm saying is, I will say the lowest one is 0. That's all. I'm just defining these like this. I have 8 different V by delta values. Let's say hypothetically I'm defining like this. That's all. Because we have to.
The jargon that we defined.
Yeah, because finally it has to be digitized, right? So we have 7 levels. You give 0, 0, 0, 0, 0, 1, blah blah blah. Okay. Cool.
It is a number of levels which you are taking. And 0 to 7 it is a number of levels which you are taking.
Yeah. Okay, so here to define the nonlinearity, we have to look at the quantizer characteristic and then define how much it is nonlinear. Okay, so here I am showing two things. One, the one in gray is the ideal, one in blue is a nonlinear thing. Okay, so let me ask you this way. So if I were to sketch this blue characteristic, that is the non-ideal quantizer characteristic, in addition to the fact that my full scale range is -1 to 1, what is the information I will need to plot this characteristic? Yeah, I can with the transition voltage I can do, or what can I use? The delta for each code. Either of them is enough to sketch the characteristic, right? But I am not actually interested in sketching the characteristic. I am interested to quantify how much this characteristic is deviating from my ideal characteristic. So how do I change this now? I have delta k. I want to see how much it is deviating. Minus delta ideal. Similarly here, that's all. So these are two things that you can do, and this is good but not great, because here my quantizer is operated between -1 to 1. In this case, let us say my deviation is something. Okay. Now let us say I go and change the range to -10 volt to +10 volt. What can you say about these values? When I initially operated with -1 to 1, I had some deviation. Now let us say it's same quantizer, I am just changing the range to -10 to +10. Then what can you say about these deviations? Will it be same or it will change? Why will it change? Sorry, why will it be same?
The ideal value should be same, and
No, ideal value, see, your delta was defined as the total range. So this will definitely increase or decrease? If I increase the, fine. See, this is basically stretched out, everything stretches out, everything increases, but doesn't mean that, sorry, 10 times is what you expect, right? But doesn't mean that the quantizer is more nonlinear. It is the same fellow, just that I am changing the reference voltages. So there is no point in looking at the absolute deviation. You have to normalize it, and it's normalized with respect to the ideal step size. Okay. Make sense? So this first one is called the differential nonlinearity. Or DNL. So this is DNL for a code K. That is a deviation in the ideal deviation of my quantizer characteristic, that is quantifying how much the step size is different from the ideal step size. So similarly, we have to give name for this. This is called the integral nonlinearity, or INL.
on what basis are we defining it to be differential integral?
Okay, I'll come to it later. I'm coming to it now. Okay. Your question is why this is called differential integral. So one simple way to look at it is this. So first of all, remember DNL and INL are explaining the nonlinearity of the same quantizer. So do you think they will be related or not related? They should be related, right?
We need either one of them, right?
We need either one of them, but each will give different info. This is oh, this is, I mean, this is the standard. Yeah, so you are asking, what did you ask? I forgot.
I was asking, we need either one of them.
Yeah. So each will give different information. So this gives a local picture, right? It says how much for each code it is different. This is giving the global picture, how much these voltages are different. They are not independent, right? If you know one, as we'll see, we can get the other, right? So here, right, let's, before going to the relation, for this quantizer ideal characteristic, recollect my Vk ideal was k minus 4 times delta ideal. Okay. So with that in mind, let's actually look at this. So let me rewrite these things. So DNL of k is delta k minus delta ideal by delta ideal. INL of k is basically Vk minus Vk ideal. Vk ideal I'll replace as k minus 4 delta. Okay. So from this, can you think how these two are related? Hint is, remember, Vk plus 1 minus Vk, what is this? It's delta for the code K. Based on these three pieces of information, can you tell me what could be a possible relation? Right? So let us say you find INL of K plus 1 minus INL of K. Right? So this will be the first term. If I write Vk plus 1 minus Vk will be there. Yeah. And this will be K minus, this will be K plus 1 minus 4 minus K minus 4. That will just become delta ideal. So this is basically delta K minus delta ideal by blah blah blah. And these are all minor algebra. So that's why it's also given this name. So to answer this question, if you see, I take the first difference, I get this fellow. Or the YC, the inverse relation is if I accumulate DNL, I get INL. So
that K minus 4 is because the 0 is at 1.
correct. Yeah, otherwise also this will be something else. But if you take the first difference, the offset cancels off. Yeah, in this case, this is the exact thing. But even otherwise, the point is it is dependent only on K. If you take the first difference, that goes off, you will be. Is that okay? Oh, accumulating meaning, see, this is okay. Right? If I take the first difference, I get this. If I want to get this from this, I should do the other thing. I should keep adding. This is basically differentiation, right? First difference is d by dt. If I map it to continuous time. So, cool. So now let's look at this guy. So here, can you try to find out what is the DNL for code 3? This is code 3. How do I find DNL for code 3? I should find the delta for that particular code minus the ideal code by delta ideal. Yeah, so what is the delta for the code 3? 0. So this is going to be minus 1. So other thing is, in principle, DNL, INL are unitless, but typically we say it's so many LSBs, least significant bit. So this is basically minus 1 LSB. So what this means is the code is not even present in your quantizer characteristic. So this scenario is often called as missing code. So if you have a missing code, it means that my DNL will be minus 1. So typically that's why we don't want DNL to reach minus 1. So you want it to be within minus 1 to plus 1. Cool. So now it turns out, in addition to the nonlinear quantizer characteristic, there is also other non-ideality, which is this fellow. So here again I am showing two characteristics. The one in grey is the ideal. The one in blue has some non-ideality. Can you look and tell me what the non-ideality is here? It's not exactly shift. Or the other way to see, here the code widths for all the codes are same. Okay. The delta 1, delta 2, they are all same, equal to some delta hat, but that is not equal to the ideal code width. That's all. So if I try to join the transition voltages, in one case I will get this as a straight line. In the non-ideal case, I will still get a straight line, but what is different? Yeah, the slope is different. So this is what,
Deltas are different.
Yeah, the deltas are same for all the codes, but that is not equal to the ideal code width. But this is not non-linear, right? This is a linear defect, and this is called a gain error, and this is not an issue at all. Just that the slope is different, right? So doesn't mean that we have non-linearity here. But if you stick to our definition of DNL, and try to find the DNL for any code, it will be delta hat minus delta ideal by delta ideal, and we'll wrongly say that, well, I have some DNL, but we saw that this is not actually non-linear. This is a nicely linear characteristic, just that the gain is different. So we have to change this definition slightly. How do you think we should change?
So delta for the last case, like,
Yeah, last case infinity, similarly this infinity. So it is not defined. We'll come to that in a minute. But before that, can you tell me how should I change this definition so that here I get 0 DNL? Huh? Yeah, basically I should not use delta ideal as my thing. I should replace it with a corrected delta. So we have what is called, we have got an average delta. Okay. How do we define is this? It's not that difficult. You just have to take into account the gain error, right? So one way to see is, if you look at the ideal characteristic, the delta was how much? 0.25, 2 by 8, 0.25. And the way to see how we can get this is, let's say this is minus 0.75, the last transition is plus 0.75. I'll just take the slope of this guy. So what I'm doing is I'm checking the difference between the two, that's 1.5, and within this span of 1.5, how many codes I have? 1, 2. So I can, again, this is a loose explanation, so I have that is basically 0.25. So now you find the delta average the same way. Now you basically take this voltage minus this voltage divided by the number of codes you have. You'll see it in some detail now, but this is what you should do. So again, to clarify these things, so let's look at an example. So here I am showing a characteristic with all the transition voltages marked. So firstly, we will try to find delta average. So delta average, as we saw, we look at these two transitions for simplicity. Okay, I have already marked the numbers, so we can directly look at it. This is minus 0.625, 0.525. So just take the difference of these two, divided by the number of codes you have, which is basically 1, 2, 3, 4, 5, 6. You will get something as delta average, and use it for calculating DNL. So again, calculation is easy. You just do it for all the codes, right? So I'll just show one example and then we'll stop. So as he was pointing out, if I look at the code width for code 0, right, any voltage from this to minus infinity is for code 0. So the code width in principle is infinity, so we don't define it. Doesn't make sense to define a code width here. Same holds good for the last code. Any voltage from this point till infinity is quantized to the code 7, so no point in defining, so we don't define here. So DNL is not defined for these two. And for the rest of this you can find out now. You know delta average, and DNL for each code you find it as delta for the particular code minus the average one. Yeah, that's what is done. Fine. Now it turns out, in addition to this gain error, there is also another non-ideality, which is not non-linearity. So I am showing that here. So as usual, the one in grey is the ideal, one in blue is the non-ideal characteristic. What is the difference? Looks like there is an offset. Okay. So this is called offset error. So again, there is no non-linearity, just that there is an offset in all the transition voltages, right? So in this case, if I try to find the INL, INL is basically the deviation of the transition voltages. I will have Vk minus Vk ideal by delta. So here it will look like all transition voltages are deviating and I have INL, right? But that is not the actual picture. So what you should do?
You will take the average again.
No, if you take the average, I mean what average you are taking? So how should I compute INL here now?
Take delta average.
No, delta is only here, right? That is just scaling it. The main thing is here.
It's a VK ideal and VK average.
No, VK average you can't take. That VK will change for each code, right? So what should I do? I mean, I have an offset. I should not have the offset. Huh? Yeah, you basically remove that offset and find it. Yeah, you basically add or subtract an appropriate offset. That's all. Okay. So in practice, you will find you will have everything. You will have offset, you will have gain error, and then non-linearity. So the here you find the slope. I mean, not slope. If you draw a straight line connecting all of them. What is the slope? No, is it compare the two slopes, right? Yeah. So which means there is no slope error. There is an offset. Yeah, slopes were different, right? If you check it, I think I erased it, but if you join it, you will see this is this, and this is this. So in practice, you will have everything like this. So the standard way is you first have to eliminate, I mean, find the offset, remove it, find the gain error, and then use delta average. So the standard way is you take MATLAB or any thing. You take all these points, okay, and try to fit a straight line like this. Basically, V is alpha naught plus alpha 1 times y, something like this. This will give you offset. You can subtract the offset. From this, you can find what is the gain error. So you can find delta average from this. And then you go and compute DNL INL. That is what is done in practice.
Sir, in the previous slide, where we had VK minus VK ideal.
Correct,
so
correct.
like we are subtracting the offset from the numerator, right?
Yeah. Yeah, correct. Sorry, I probably should have, I had it incorrectly. The fraction is like this. Is that okay? So in practice, you eliminate all the linear defects which are offset and gain error, and then you compute non-linearity from this. And this is what is done to characterize the static non-linearity. That is to see how my ADC is behaving for DC signals. Okay. So that kind of winds up the discussion on system level aspects of ADC. So at this point, if you take an ADC datasheet, you should be able to figure out what each spec is and know what it means. And if you have an ADC, you will be able to measure and characterize its metric. So from now on, we'll start looking at circuit level aspects, the circuit design things. So
including gain error, offset error, and non-linearity, you will say that ADC is non-linear.
No. Non-linearity is only due to, non-linear is due to only non-linearity, right?
So these are the static non-linearity.
Yeah, yeah.
So we will not include this gain error and offset error in the non-linearity.
That is not a non-linear phenomenon. That's a linear phenomenon. It's a straight line y equal to mx plus c. Just that m is different from what you want, c is not 0.
So non-linearity characteristics of ADC just comes from the non-linearity part which you have seen.
Yeah, non-linear part.
Like we have seen
Yeah, that
from that part.
yeah.
Like because of the non-linearity quantizer, we call it a non-linear ADC.
Correct. If you, like I told, if the code widths are not equal for every code, that is non-linearity.